everyone, this is Miss Cantwell. I hope that you're still doing well and that you are able to find some time to kind of take care of yourselves and de-stress, and also that you are able to complete your assignments. If not, just please remember that we're always here to help you at any time. Okay. If you haven't completed last week's quiz, feel free to go ahead and go back and complete it. We will update your grade as soon as we know that you've done that. For this week's Edgenuity material, we start getting into nuclear physics. So we're going to talk about radioactivity, and we are going to talk about nuclear power a little bit. So let's go ahead and get started. So the basic structure of an atom is something you've been learning about for a long time in science. We've got our nucleus that has the protons and the neutrons, the positively charged particles and the negatively charged particles, and those are sandwiched together in the nucleus. And then we've got our outer area. Sometimes it's called the sea of electrons, sometimes they're orbitals. It just depends on what model we're looking at. And that's where the electrons are. The electrons are much, much smaller. They're negatively charged, and they hang out outside there. The protons inside the nucleus don't like each other, right? Because like charges are going to repel. So the protons try to get away. And there is something called the strong nuclear force that actually keeps them together. And the more protons that we have, the stronger that force has to be. Okay, so we can see that as we get more protons, okay, as the number of protons goes up, then we are going to need more neutrons in there, a stronger nuclear force to hold it together. And if that number of protons gets way higher than the number of neutrons, then we start to get something that is not really stable anymore. So it's not stable. It will actually try to fix the problem like nature does, right? Natural things try to maintain stability, so they will try to fix the process, and it'll go through radioactive decay. So there's three radioactive decays that we talk about. This, if you look at this graphic here, the alpha decay, you can see that we've got uranium-238. It decays into this element, and then a helium. Okay, beta decay. We can see that the nuclear or the neutron number doesn't change, but the mass number does, okay? And it is a new element, and then also this other particle here, okay? So for the alpha decay, when it decays, it moves the atom down and leftward on that stability curve, and in beta decay, it moves it down and rightward to get more stable. Real quick, you won't be assessed over any of that I just said. What you will need to know is that alpha decay is when we get a new element. Okay, we lose some mass. Alpha decay can go through a sheet of paper, okay, but it's going to be stopped. It's stopped by a sheet of paper, so it can't go very far. It's not usually dangerous unless you ingest the products of alpha decay. It's the weakest form. Beta decay will go through that paper, but it gets stopped by a sheet of aluminum foil. It's going to emit a beta particle, which is either an electron or a positron. It will have either a negative or positive charge accordingly. You'll get the same mass number, but it'll be a new element. And again, it's going to be stopped by that sheet of aluminum foil. Gamma particles that's the most energetic. okay? What we're emitting here is a photon, and it's not going to have any charge, but we are going to lose some energy. So gamma particles can go through paper. They can go through aluminum foil. They can penetrate concrete. So when we're working with gamma radiation, which we do sometimes, even though it's dangerous, we can work with it and kind of harness it and focus it to make it useful to us. So there are two other categories of radiation. There's non-ionizing. That's low energy and not harmful to living tissue. So like there's radiation all around us. Particles are decaying all around us, but a lot of it is non-ionizing and will not damage us. Ionizing radiation, like alpha, beta, and gamma decay, that has enough energy to damage living tissue. So you can see here, this is an let's see. Looks like they're doing fluoroscopy. So it looks like they're removing a fish hook in this patient's hand, and they need the x-rays to see exactly where it is so they don't damage anything. So they're looking at her hand on that screen, but you can see that the technician that is taking the x-rays is wearing a lead vest so that he won't absorb any extra radiation. You've also heard of people going through radiation for cancer treatment. So that is something that is dangerous, but if they focus it in just the right place, they can actually use it to kill the cancer cells and eliminate them while preserving the healthy tissue all around. So if you know anyone that's been through radiation, it's a very, very focused, short burst of radiation. Okay, so radioactive materials and isotopes have something that we call a half-life. It's the rate that they decay. So it's the amount of time that it takes for something to decay by half. So this is kind of the table that they showed you in Edgenuity. When we first start out, we have 100% remaining. After one half-life, we have half the material remaining, so it's 50%. After two, we have a quarter of the material remaining, that's 25%, and so on. Okay, so if you were asked to solve a problem, okay, the half-life of iridium is 15 minutes. How much of a 1 gram sample is left after 45 minutes? So let's get a color. So half-lives, 0, 1. So the time after one half-life, that's 15 minutes. After two half-lives, that's 30 minutes. After 3 half-lives, that's 45 minutes. So this is the row that we need to focus on, right? So we'll have the fraction of the sample. It's going to be 1, okay? After that first half-life, there'll be half of it left. After that second half-life, half of a half is 1/4, and then half of a fourth is 1/8. So there'll be 1/8 of it left. So if we start with a 1 gram sample, 1/8 times 1 gram is 0.125 grams. So it's really just as simple as remembering that half of the sample is going to be gone after each half-life, okay? And we wouldn't ask you any questions about any that are like between half-lives or anything like that. Okay? So let's go back to here. That's some cat shenanigans that needs to stop, I'm sorry. All right, so nuclear fission and nuclear fusion. These are both ways that we can make, well, not we, but that energy can be produced. So let's just look at it. Nuclear fission, this is the thing that we can do on Earth. This is when we split the nucleus into 2 smaller nuclei. So we actually make two things from it. And because that nucleus is held together by that strong nuclear force, when we break it, it releases large amounts of energy. And so this is what nuclear power plants will do. If you look we've got a neutron, we've got an radioactive isotope here. That isotope splits, so we have the two byproducts, and then we have lots of energy here, and it actually will form a chain reaction for the rest of the sample. Okay, so a nuclear fission reaction would look something like this if you were to see it on a formula. Okay, so you can see we've got that uranium-235 and the neutron, not the neutron, I'm sorry, this particle. When we collide those together, we get a barium isotope and a krypton isotope, and then 3 of these particles. So you can see that we start off with one big thing, and then we get 2 smaller things. Same with this second example, one big thing, we get 2 smaller things. Okay, so that's how you would know it was fission, is if we break one big thing into 2 small things. Oh no, it's taking forever. Here it comes. Okay. So then, we bombard the nucleus with the neutrons, and then it causes it to split. So just like this image shows you, and just like the equation shows you. Energy produced by nuclear power plants has lots of advantages. There's low pollution. There's very little emissions or carbon emissions produced as a byproduct. You get a lot of power for a little bit of material. Of course, there's also disadvantages, and that is what has kept us from exploring this as a larger source of our power in the state of Texas. And then also, we've got readily available natural gas and petroleum, but it is something that is utilized quite a bit in some areas. The technology for it now is really good, so that if we're following the protocols, there's a very, very slim chance of, slim to none, I'd say, of the Chernobyl type disaster. The other thing that people worry about is the byproducts. What do we do with the radioactive byproducts that we can't use anymore, but we can't just dump them in the environment because it'll destroy the environment. But they do some things with like lead shield and concrete shielded deposit places. Really, at this point, I mean, it's good. It would be a good thing to look into as far as safe and clean power. Okay, fusion is when we combine 2 small nuclei. Okay, so here's an isotope of hydrogen, here's another one. We combine them together, and that's making a new new element. So it's a helium nucleus, and it releases that extra neutron that was on this hydrogen 3. It also releases a large amount of energy. So because this neutron gets released, it becomes that energy. Okay, so this one requires a lot of pressure and very, very high temperatures. So it's stuff that's done very easily by stars, but it's not something that we're able to recreate here. Okay, we can not get the pressure high enough on Earth to replicate that. We would have to compensate with generating really, really high temperature reactions, and we just can't get them hot enough to make this happen. So let's look at what a reaction would look like for fusion. So you can see here we've got these 2 nuclei, or these 2 nuclei. We get a helium atom out of it, a neutron, and then lots and lots of energy. So this is the idea that, Einstein came up with this formula. Okay, E equals mc squared. E is energy, and m is mass. Okay, so we can see that energy is directly proportional to mass. That means if we decrease mass, losing that mass is going to give us lots of energy. And this is something that kind of goes contrary to what we think, because we know that the amount of mass is conserved and the amount of energy is conserved. But this idea here of relativity, or of mass energy equivalence, shows us that we can lose some mass like we do here. We have, and that mass turns into energy. And so the kind of coefficient or whatever is the speed of light, which is really, really big. So it is directly proportional, but you have to multiply whatever mass is lost times the speed of light to see how much energy you would generate. And you can get a lot of energy from it. But again, this is a process that we aren't doing here on Earth. This is stars mostly that are doing this process, and that's how we get new elements. So we start off with just hydrogen, and then helium. We fuse a hydrogen and helium, we'll get something else new. That's how the elements on in the universe were first formed, was through nuclear fusion, not something that we can do here on Earth. Okay, I hope this has been helpful. I hope that you are staying safe, that you are taking care of your physical and mental health as well. If there's anything that I can do to help you, if things have changed at home, just let me know. I'll do my best to help you and try to figure out ways that we can work around it. And just remember that that we care about you, and that we're here for you. Okay? Thank you so much for watching.